Resistance to muscle contraction in strength training exercises is generated by 5 primary sources: gravity, inertia, friction, fluid resistance, and elasticity. Each source contributes differently to the force and power demands of exercises, and understanding these factors is key to selecting appropriate training methods and equipment. Gravity is the most straightforward source of resistance, defined as the force that pulls objects toward the earth, equal to the object's mass multiplied by the local acceleration due to gravity. For example, when lifting a barbell, the force needed to move the weight depends on the mass of the barbell and the gravitational pull acting on it. Interestingly, the actual weight can slightly change based on location because the acceleration due to gravity varies globally. Free weights such as barbells or dumbbells primarily use gravity as resistance, but the moment arm, the horizontal distance between the weight and the joint, determines the torque that muscles must generate. In exercises like bicep curls, the torque is greatest when the forearm is horizontal, requiring the most muscle effort. Inertia refers to the resistance to changes in motion. When lifting or accelerating an object, inertia adds resistance because the mass resists any changes in velocity. Olympic lifting exercises, such as the snatch and clean, require athletes to overcome not just gravitational resistance, but also the inertia of the barbell as it moves upward. For instance, when a power clean is performed, the lifter applies force to accelerate the barbell from rest to a high velocity, increasing resistance at the start of the movement. This creates a unique training stimulus since the bar's resistance decreases slightly toward the end of the lift as velocity stabilizes. Using inertia as a training tool also allows for neuromuscular adaptations, particularly in explosive sports where acceleration is key. So, frictional resistance is generated when two surfaces interact, impeding motion. Devices like cycle ergometers, which use friction between brake pads and wheels, rely on this principle. In such devices, resistance remains constant regardless of movement speed, making friction useful for endurance training or controlled resistance. However, friction-based equipment is less ideal for movements that require variable resistance. An example of friction and resistance training is using a weighted sled. Athletes often push sleds across different surfaces, creating a combination of friction and inertia resistance. The friction between the sled and the surface, e.g., grass or sand, affects the force needed to initiate movement, with static friction being higher than sliding friction. Once the sled starts moving, the force required decreases slightly, maintaining a steady resistance throughout the exercise. Fluid resistance arises when an object moves through a liquid or gas, or when a fluid moves past an object. Machines using hydraulic or pneumatic resistance are popular for low-impact exercises, particularly in rehabilitation. These devices rely on the movement of pistons through fluid to generate resistance, which increases as the movement speed increases. For example, hydraulic resistance in machines like a chest press provides more resistance when the user pushes faster, simulating variable resistance in a smooth, controlled manner. However, one limitation of fluid-resisted machines is their lack of eccentric muscle action, a key component of many sport movements like running or jumping. Without the eccentric phase, fluid resistance training may not perfectly mimic sport-specific demands, but it's highly useful for controlled resistance and rehabilitation purposes. Elastic resistance found in bands, springs, or other flexible materials increases as the material is stretched. The resistance offered by elastic bands or rods is proportional to the stretch distance. In this setup, resistance is minimal at the start of the movement and increases toward the end, opposite to the typical force production pattern of human muscles. For example, during a resistance band squat, the band provides less resistance at the bottom of the movement when the gluteus and quadriceps muscles can exert the most force. As the athlete ascends, resistance increases, potentially leading to suboptimal force application near the end of the range of motion. Despite this drawback, elastic resistance is convenient and portable, making it useful for home workouts or rehabilitation. While resistance training poses fewer risks than many other physical activities, such as team sports or running, it still carries some injury potential. Studies have shown that resistance training has a relatively low injury rate, with about 4 injuries per 1,000 hours of participation. For comparison, running and aerobics tend to have higher injury rates, while cycling and walking tend to have lower ones. To minimize injury risks during resistance training, it's essential to focus on specific joints and movement mechanics, particularly the back, shoulders, knees, elbows, and wrists. The human back is particularly susceptible to injury during lifting due to the structural and mechanical challenges of the spine. Unlike quadrupeds, humans stand upright, placing compressive loads on intervertebral disc even during simple activities like walking or standing. These forces dramatically increase during lifting and carrying exercises. For example, in exercises such as deadlifts or back squats, significant torque is exerted on the lower back, especially when the trunk is inclined forward. This creates a large horizontal distance between the weight and the lower intervertebral discs, which must be supported by the spinal erectors. Because the muscles of the back act at a mechanical disadvantage, they often need to generate forces up to 10 times the weight being lifted. To reduce injury risks, athletes should maintain a neutral spine during exercises. A neutral spine means that the lumbar region remains in a slight arch, a lordotic position, rather than a rounded set kyphotic one. A lordotic position has been shown to reduce the compressive forces on the L5-S1 intervertebral discs and the associated ligament strain. Furthermore, intra-abdominal pressure, often supported by the use of weight belts, can provide additional stability to the spine. The fluid ball created by contracting deep abdominal muscles and the diaphragm reduces the strain on the spinal erectors. However, improper use of the Valsalva maneuver, where the athlete holds their breath during a heavy lift, can lead to elevated blood pressure and strain on the heart. Lifters should be aware of how to build intra-abdominal pressure safely without excessively increasing chest pressure. The shoulder joint's wide range of motion, combined with its relatively shallow glenoid cavity, makes it vulnerable to injury. Resistance training exercises like bench presses, shoulder presses, or snatches can subject the shoulder to significant forces. Because the shoulder is a ball and socket joint with considerable mobility, it relies heavily on muscles, tendons, and ligaments for stability. Rotator cuff muscles, supraspinatus, infraspinatus, subscapularis, and teres minor, play a key role in maintaining shoulder stability. Overloading these muscles, particularly in repetitive exercises, can lead to tendinitis, rotator cuff tears, or impingement syndrome. Athletes should ensure that their shoulder workouts are balanced across different movements, e.g., horizontal and vertical pressing and pulling, and emphasize both strength and mobility. Knee injuries in resistance training often result from excessive torque or improper technique. As the knee sits between two long levers, the femur and the tibia, it is vulnerable to forces, especially in exercises like squats or lunges. Unlike the shoulder, the knee primarily moves in the sagittal plane, flexion and extension, with limited rotation. Injuries often arise when excessive frontal or transverse plane forces are introduced, such as when a lifter's knee caves inward during a squat, valgus collapse. The patella or kneecap increases the mechanical advantage of the quadriceps by holding the tendon away from the knee's axis of rotation. However, repetitive high-force activities like squats or running can lead to patellar tendinitis, which manifests as pain and inflammation in the patellar tendon. Proper progression in load and recovery can mitigate this risk. Knee wraps are commonly used in powerlifting to provide support during heavy squats. Research suggests that heavy knee wraps can increase squat performance by adding up to 25 pounds of lifting force through a spring-like effect. However, the overuse of wraps may limit the development of the quadriceps and surrounding musculature, potentially increasing injury risks when training without wraps. Overhead lifting exercises place stress on the elbows and wrists. However, the risk of injury to these joints is relatively low compared to other areas of the body. Injuries like dislocations are more common in overhead sports, such as gymnastics, rather than during weightlifting. Repetitive use injuries, such as tendinitis, are also common in sports like tennis, but can also occur in weightlifting with poor technique or overuse. A specific concern for younger athletes is epiphyseal plate damage, as their growth plates are still developing. While resistance training is often discouraged before growth plate closure, recent research indicates that it can be safely performed under supervision without causing injury. The risk of injury in resistance training is generally low compared to other sports, but careful attention to biomechanics can reduce it further. Using proper technique, maintaining balance between muscle groups, and taking precautions like using a weight belt or knee wraps when appropriate can help prevent injuries to the back, shoulders, knees, and other joints. A well-structured resistance training program tailored to an individual's needs and capacities offers numerous benefits while minimizing injury risks.